Again, my name is Mclntosh, and we're going to talk about patch diffing on StarOS today on Apple. So I'll first thank Objective by the Sea, again, for having me here. I'm proud to be here among all the amazing speakers, and I hope to share some of my research over the past year, me switching from Windows to Apple, and what we've learned along the way. So a quick who am I? You'll find me on social media at ClearBlueJar. I'm a security researcher generally. I have founded a small company called ClearSec Labs. I'm an open source dev. You'll see some of my tools mentioned here during this talk. I'm a speaker sometimes. I'm a blogger often. And about 4 years ago, I wrote a tutorial called CVE North Stars. And that's where I taught myself how to do patch diffing well with Ghidra, kind of learn the ins and outs, and I shared that as a tutorial online. So real quick, let's get everyone on the same page for binary diffing and what it's useful for. Binary diffing is really just comparing two binaries together and finding what has been added, deleted, or modified. And those differences kind of highlight interesting things about a binary, about what has changed. Generally, for our kind of security subject, we can use binary diffing and reverse engineering to help port our changes. Say you were 85% done reverse engineering a binary, a new version comes out, you don't want to repeat that work, you can use binary diffing to match those functions up and save you some time. For vulnerability research, and this is our primary topic today, how can we use diffing? We're going to look at diffing to see like the binary truth, or to see what has changed about a binary and see if they fixed it for real or if it's just a shallow fix. You can also use it for malware analysis. If you find some functions that are similar, you can do some lineage correlation there. But this is the screenshot of the tutorial that I wrote. And the main idea was that to leverage CVEs as a compass or a map to vulnerable code. And so using CVE as a North Star in your vulnerability hunt. I had this kind of big graph about doing CVE research, coming down, combining that with some analysis, doing some root cause identification, and finally getting to a point where you can maybe find a variant or do something for mitigations. The main three truths I pulled out was that patch diffing is this single source of truth. You don't have to find a blog post or a write-up. You can go and see for yourself what has changed, that binary truth I'm talking about. And then you can also get some clarity in the root cause, like what is the issue they actually fixed and did they fix it well? And as you'll see as well with our examples, it's kind of a fun weekend project. You can take a CVE and say, hey, can I reverse engineer this and build up your skill as you go. So I wrote a command line tool. It's open source. It's called Ghidra. It uses Ghidra. We'll talk about that here in a second. But it allowed me to really quickly do binary diffs on the command line with, this is an example of me doing this on the Windows kernel. I know we're not supposed to talk about Windows here, but this is what I've been primarily doing. And I would post things on Twitter, just kind of like, look at this bug here. You can see this clearly in the diff. And I got really good at doing this on both Windows and even on Android. And so what this talk about is more, how do I systematically do patch diffing on Apple? And so we're going to go through that journey together. I'm going to teach you guys that process as we go forward. So what's different on Apple versus Windows? And some of the general things are just, how do we get binaries? That's different from Windows than on Windows or Android. The Apple ecosystem is different, and that was new for me. I'll see that here throughout the talk. And the file system layout, you'll see that as we go. So the basic patch diffing is the same. You want to find the patch binary, the vulnerable binary, use some type of SRE tooling, do the diff, and finally get to the root cause of the issue. That's a hope. You can't always get there. If we look at some previous diffing research, Stefan Esser here is talking about a jailbreak that he reverse engineered with IDA and Diaphora. And what's different about this talk is that was an expert Apple researcher, and today you just have a researcher before you. That was IDA and Diaphora, two different tools. We're going to use Ghidra, my tool Ghidra, and IPSW, which is a way to, I'll explain here in a second how to look into IPSW files. We're going to look at several CVEs as the example here. So here we go. We're going to use patch diffing to open up this gateway to this Apple security ecosystem. This was new for me at the end of last year in 2023 when I started doing this. And it's been helpful so far, and we'll learn together. We're not the giant here facing Apple. There are some giants in this room, but we're that little person leaning on the giants to see what we can learn as we go along the way. And so here we go. That was my intro, so I got 20 minutes left. Let's see what we can do with this whole talk. So high-level diffing on StarOS. Now, I got a lot of slides, but I'm going to get through them quickly. All right, so what's the diffing strategy? We're going to look generally at different OS builds. We're going to compare the binaries across the OS version. We're going to ignore most of the changes because there's thousands of changes. We're going to focus on a single CVE to kind of focus our reverse engineering effort. And this is the big high-level diffing process. This is for your slides later, or for your note later. And then so let's begin. So where do we find CVEs? We have to go to the Apple security updates. This is much like, again, me coming from Windows, like a Patch Tuesday, but Apple has to be different. They release on Monday, and I'm dating myself a little bit, but these are the advertisements I grew up with Apple trying to separate itself from Windows. So updates in general, remember they're a double-edged sword. They fix the issue, but they also point out the issue, and that's what we're going to do with our diffing today. And this is I'm quoting myself here, but a security patch is a form of vulnerability disclosure that is always public. If the binary can be reverse engineered, then that disclosure will be public. So let's begin. We're going to start with the Apple security release. And this is the main page there. You can go and select one of the devices you want to look at or operating systems. You choose a specific build, and it will list off all the CVEs that were fixed in a particular build. And so from that list of CVEs, we can select one and use that as a starting point for this adventure that we're going on together. So we can, from the Apple security update, identify a CVE, but we have to get all the files. So which files have changed and which files relate to that. And for that, we can go to IPSW. And IPSW is how Apple wraps up its entire operating system in a single file and distributes that across all the updates. You can go and download one of those IPSW files. You can use IPSW.me, a third-party site. You can choose a platform, choose iPhone in this case. You can drill down to a specific build, and then go ahead and download the 8 gig or 13 gig IPSW file that will contain all the files for that update. The URL itself will give you some information about like the device, the version, and the build, and from that information, we can start to build our case for patch diffing. If you take one of the IPSW files, and it's actually just a zip archive, you can change the ending there and unzip it, and inside there will be several disk images that were very confusing to me when I first looked at this, and there still are. But we have a tool to fix that. But the disk images, they're only the base file system. They contain all the files in the base file system. They have the DLD shared cache in there, and there's also the kernel cache. These are all available to you within the IPSW. These are all things we need to go look in when we're doing our patch diffing. But again, how do we make sense of all these files if you're new to Apple? Luckily, you don't have to understand every single part of it. There is a tool out there called IPSW, and it is amazing. This is why I'm probably standing here today, confidently able to parse through all these files. And the point is that IPSW, the command line tool, speaks fluent IPSW, so again, we don't have to. Its tagline is that it downloads and parses IPSWs and does a lot more. And here's a big list of all the things that it will do. But we're just going to talk about how IPSW can download IPSWs, it can parse them, and it can extract the files that we need, and also do the diffing of the two files together. So here we go. How do we diff the IPSWs? Here's the questions that we need to answer. And all those questions are answered with IPSW, but how can we download the correct ones? We have to match the patch version and the one before. How can we extract the files that we need? Again, IPSW to the rescue. Here are all the commands you would need to do all of these things. I've just listed them here so you can follow along the work later. But if we want to go and download an IPSW, we can use the download command. So IPSW download, we select a device that we want to go look at, and then we can select a particular build that we want to download and OS. And then from there, you can list all the available IPSWs and choose the two that you want to go and download. You want to download the one that's patched and the one right before. I call it the N-1. So here's some example commands you can run. And then you run IPSW diff once you have the download complete. So this IPSW diff spits out some amazing output here in Markdown. I'll show you in a second. But it extracts all of the disk images. It does the comparisons for you. And so all that hard work of understanding, where are these files located, how do I extract the DLD shared cache is taken care of for you. And in the end, it outputs this Markdown format where you can see all the changes that have happened kind of across. And this will tell you what binaries have been updated, if there's entitlement changes. This was a picture, a snapshot from December 2023 when I first tried this. And this is kind of like the high-level view. It gives you the kernel cache information, it gives you entitlements, and the DLD shared cache. It was actually missing something that I needed. I needed to see the difference in the MacOS binaries that were there, and that was something I needed for diffing. And so my first attempt actually failed. I tried to diff a system application. I couldn't see any differences or changes because they weren't listed in the IPSW diff. And the actual diff failed itself. And so that didn't stop me, though, because I then went to the repo, and Blacktop, she's amazing. I put in 3 issues, and she fixed them within 3 days. She came along, said, oh, yeah, those are pretty critical, and she fixed them all. She added the Mako changes. She she actually started to talk to me about a lot of how the file system works. I was able to ask her a lot of questions. A lot of the insights I have now have come from my building my relationship with her. And she introduced me to a Discord channel called Hack Different, which I was unaware of before. And that's, again, where maybe the title of the talk also came in as well. But it's a cool community. Probably, I assume some of you are part of that. So she made the changes. I was able now to see the differences between the macro files, and that's the new center, or the diff there. I would click on this, but I don't have internet. I can't actually show you it. But here we go. We've identified a CVE. We can download IPSWs and parse them. We can look at the changes by looking at the diffs that have come out. And so how do we then go and look at how do we diff the binaries themselves? So in order to get the binaries out, we still have to extract them. The diff just shows you all the differences. So you still have to go and extract the files. So you can use IPSW extract. And then basically you're searching for your file, maybe in the root file system, maybe in the kernel cache, or maybe in the DYLD shared cache. Again, if you were inexperienced like I was, or probably still am, you can use the IPSW diff to help you find it. If you can't find your binary, you see a path name in the IPSW diff, and you can't find that binary, it could be in the DYLD shared cache, especially if it's a framework or private framework. That was something that was new to me last year. And again, the diff result itself will show you where the binary should be, whether that be in the kernel cache, a Mako file, or on the DSC. So as we're continuing along now, we've gotten through most of this, but we still need to figure out how to map binaries and actually look at some CVEs. All right, so we're going to actually look at Ghidra, which I think is maybe not as popular as IDA or Binja, maybe for Apple, but I studied Ghidra quite a bit. I'm going to show you kind of what Ghidra can do and what it's capable of. If you look across the change log for Ghidra, there's 88 mentions of something to do with Apple since the beginning. Actually, it's released in 2019 until I think this was about March, so there's a few more now. But it's always supported Mac, but it's been lagging. So what can it do? There's a reference in the Apple Wiki about how Ghidra can handle the DYLD shared cache. I did a quick experiment in January, and it was able to parse the 6,000 or 6,700 files out of the DYLD shared cache. And actually, it just took about, I don't know, 3 or 4 hours, I feel like. And I just left that going overnight, and it did work. But just because we have a short presentation, I just have some quick tips. If you're doing analysis with Ghidra, make sure you tick on this decompile parameter ID set to true. And my next tip is go ahead and steal types from IDA. So people have published some types out there you can load up into Ghidra. And then it kind of changes your types, again, from something unknown to something that you can actually reference in the decompilation here on the right side. All right. So quick touch on Ghidra, importing the binaries. One more thing, if you are new, switching over from Windows to Mac, these universal binaries were confusing to me. Why are both in there? It's because it supports both architectures. Ghidra can handle importing the files, and they'll just list both the ARM binary and the x64 binary. Just remember just don't forget about those when you're parsing. IPSW has a tool that will extract that for you if you want to use. Or can you just use the LiPo tool that's available on Mac? All right, so we can analyze binaries, we can import them, and now we'll get to the actual diffing of the binaries. Again, we're going to use Ghidra for the diffing through my tool, Ghidra. And basically, back in January, I started to, teach my tool how to handle Mac binaries well. And I made a new release so I could support Apple. It wasn't too many changes. It's still using Ghidra and the standard kind of diffing algorithms to do this. But now we can do something where I say Ghidra, old binary, new binary, and produce something that looks like this. Now, this is another markdown output, and it's hard to see from where you are, but there's a small section of added functions, modified functions, and things that are really helpful for quickly looking at changes across the board there. So we can diff the binaries now with my tool, and now we'll dig into actually looking at the CVEs. So high-level root-causing CVEs, things to look for is like look for integer type changes or additional checks. The control flow could have changed. There could be different unsafe APIs that were removed or replaced. Or sometimes they fix it by just saying, hey, this is not a security boundary and it doesn't count. Those are all things to look for. Again, just focus on the changes. We're leveraging diffing for this aspect. And just a high-level thing is IPSW gives us insight into what files have changed across builds, and Ghidra shows us what code has changed. So with those two things, we should be able to narrow down from a CVE down to a root cause or an issue here. So I've got several CVEs to show you. The question mark ones are if we have time. Oops. And then So here we go. Let's start with the first one. CVE 2023, this is the first one we're going to look at, 32412. This was actually a Project Zero report, but in the Apple Security Update, we can see that in the telephony component, there's a use after free issue. So we can go and download the IPSW, the patch version, and the N-1. So we go find those two files. We go ahead and download those. We can repeat that later. And then we can use the IPSW diff to see which files actually have changed. And so in the IPSW diff, I think I can show you maybe just one sample of that. So in the IPSW diff, you can go and click on like what's been updated, scroll down, and you can see the actual files that have been updated and what sections have been updated within the IPSW. And that's how you determine which files have changed. And so you go through that list, and you try to map something that goes to telephony in this case. So again, how do you know which binaries map to a CVE? And the answer is you don't. You have to kind of figure that out based on a few things that might be experience, it might be a keyword. We're going to use a keyword in this first example here. But the power of diffing is that it helps you ignore everything that has stayed the same, and you just focus on those things that have changed. So again, if we look at this telephony thing, we can actually run a simple, like using the diff that IPSW produced, I'm just grepping for the word tele or telephone, and out of there comes 8 binaries that pop out of the full list, and the list is like 100 binaries long or more. And so that's still quite a few binaries to diff, but you can get through them pretty quickly with the command line tool, and then you can actually use the diff file to say, okay, where are these binaries located? Are they in the file system? Are they in the DYLD shared cache? And the IPSW diff will help you figure that out and navigate that. So you can extract the files. I won't go into all the commands there, but that's for the slides. You can finally get to diffing the CVE. So I found the file that was relevant, and actually this one was actually mentioned in the Project Zero report. But I can do the diff, and I can see the output there, and there's actually only a few functions that were added and about 4 functions that were modified. So out of thousands of functions, only having to review 4 or 6 total is pretty good. And once I saw that for the first time, I felt, yeah, this is possible. We're going to do this. I'm going to continue that down this path. So we're going to root cause the CVE. This case, we had a Project Zero report, so it's actually pretty easy. We're going to follow exactly what Ivan has said. There's a use after free vulnerability in this dylib in this exact function, so in decode. And with this issue, there's an issue that once this header is added, it's freed manually, then once again during the destructor. You can go into Ghidra and you can see that this add header function being called, and then there's it being freed here manually once, and then also in the destructor, which I don't show here. But this is a cool thing. This was, Ivan saying the fix for this is to add a merge header, for merging. This function clearly does not exist, but if you look at the diff, this is the exact function that was added in this binary. And so Apple, in this case, followed Ivan's advice and fixed the vulnerability exactly how he said. And so what we proved with this first diff is that, the root cause was still in the P0 post. We found the right file, and Ghidra handled the binary pretty well. Those symbol names were there. It's pretty easy to read. And we could detect the differences, again, and they followed Apple's advice. So let's keep going. We're going to go a little bit faster because we're getting low. All right, this is a core crypto issue. This is a timing side channel issue was addressed with this CVE. Again, we'll download the patch in the N-1. We'll do the IPSW diff. We'll take a look in here, and this time the keyword is going to be crypt. And so I'm going to use crypt to build this long file list, and there's still quite a few in there. And this time we're actually going to narrow it down. Which files actually contain symbols that are related to words in the CVE description. So if I grep for the word PKCS1, which is a word that was in the CVE description, there's only two binaries that actually contain symbols that are related to that. So that just saves you some time maybe for diffing. So which files actually had code changes? If you look in the IPSW diff, it will tell you if the binary actually had text section changes, which means code changes. In this case, this CS crypto or X attribute crypto binary had no text section changes. So when I did the diff, there were no changes found. On another binary, libcore crypto, that did have changes. And in there is my resulting diff, which you'll have a link for later. But if you look at the diff here and the decode method, On the left-hand side, you'll see some complicated math going on. On the right-hand side, you'll see a new API call called decode safe. And if we think about timing our side channel attacks, those are leaking information based on maybe the type of input. So the processing time might be different based on input, and that could leak information. So maybe they fixed it then with this decode safe function. So that's a quick review of this CVE. We noticed this time that there were more than one file change. Some files were changed, but they didn't have any code changes. That's something to be aware of. And then they fixed this maybe complicated or a variable function with a safe API function. All right, next we're going to look at CVE 2023 42942. This is from Mickey Jin, who I think is in this room, and I'm going to talk to him about this one later, but he can follow along here, see if I've got this right. So in this case, Mickey had published a blog post, and this is like the perfect example. You have a detailed blog post, there's an exploit POC, and Mickey's even commented on the patch. And so I'm like, I've got this. I'm going to get this right. High level, what this looks like is, you copy this XPC service to temp, you create an XPC connection with some legit service. Essentially, you're passing a symlink. It passes its checks, and you change the symlink to a malicious package. And read the blog post. It's way better than what I just said there. But Mickey commented on this patch, saying this has been patched in 14.1. In the copy callback function, it will check the destination path. So I'm like, okay, I'm going to go see this in my diff. And so there was some, I guess, I was trying to understand. I didn't find that result. It comes down to. Basically, they added a check here to copy file to make sure that it wasn't a symlink. That was the patch, or the suggested patch. But when I went to go look at that in my diff, actually right here, I found that the copy file callback wasn't changed. And I looked back in time further, and that actually wasn't the issue. And I thought maybe my tool was having an issue, so I checked bindiff. Bindiff kind of came to the same result for the file, meaning the symlink changes weren't there. So I'm like, is Mickey wrong? But he's not wrong. But let's keep going. The truth is it a bit more subtle, or at least I finally came to the understanding after reverse engineering this, is in the vulnerable version, it's probably hard to see where you are right now, but there's a yellow highlighted block right there, a basic block, and that's the success path. In the vulnerable version, I saw that there were two paths to success. And the two paths to success is either you pass the copy file check, or you fail the copy file check. And in both cases, you have a path back to success. And in the patch version, there's a single one. It checks the copy file path appropriately, and then it goes down to the success path. And I think that's actually what Mickey said in his blog post, but I just confused myself in the beginning. Here's the code diff. On the left-hand side, you can see the complicated, if you fail the copy file, you might still end up going to success, or you might be going another way. And the other one, you have a single if statement. But all of this was done, with Ghidra, with doing the diff and mapping the binary to the CVE itself. This root issue is, I think, and I'm talking to Mickey about this later, is the code had a path to get back to success after failure. But just in case, you can't always trust static analysis, and you want to go down to dynamic analysis path. You want to make sure, like I ran Mickey's exploit, I was able to manipulate the return address, manipulate the return value for copy file to follow that path I talked about before, which I'll show you here for time's sake. And it was able to go down this path and head back to success. And so I think I've nailed that one down. So we started with a ton of info for this one. We used Ghidra analysis and diffing to dig deeper. And we leveraged dynamic analysis in this case to find this possible root cause path. For time's sake here, I'll do this one quickly. This was an example of an issue with the TCC. And here's an example of when diffing doesn't actually solve your problem. In this case, IPSW showed me that there was a new entitlement added. So there was no binary changes, but an entitlement added that actually protected this TCC issue. And again, there was no easy way to map the binaries for this CV description. It was too broad. And basically, diffing can't overcome inexperience, but it can reveal it in this case. But there's different things to be aware of. It's not just binary changes. It could be entitlement changes. Apple is a big security ecosystem. There's a lot to learn for me, but doing this diffing brings us forward, or brings us to light. And so you can kind of see this as you go forward. Real fast integer overflow issue. This was in iOS. This was processing an image may lead to arbitrary code execution. And this was a case where there was a third-party library being used by Apple that had an issue. And the issue was here. The integer overflow with this library, and with Apple using this, Apple's also vulnerable. And so you can see the fixes, kind of going quick here. You see the change in the release, and then you can actually see the fix with the diff here, where they changed a signed integer to an unsigned integer to fix the issue. You can compare that to the source code change. And again, this is another example. I've included all the links for time, if you can follow this step later. But this was a third-party library issue that we could diff and also find the same issue there. So I think I'm just about out of time, but I have some quick pictures. I can do this. I can do it. All right. So conclusion. You can leverage patch diffing to kind of, again, open this gateway to the Apple security ecosystem. And if you're new coming into Apple, I think this is a great way to do it because you jump in. You can lean on the giants. You can do the diffing. The diffing will just highlight the things that have changed that are important for that reverse engineering piece. And so you can build your own RE adventure just by choosing the CVE. Again, tonight, you guys are bored. I recommend it. Again, I said this before, but lean on the giants. The blog posts that are out there from the people in this room are really helpful for learning and understanding. Try to repeat that work, and you'll figure out where you don't understand, and that'll kind of come along the way. Ghidra can handle Apple, but we can talk more about that offline of how to improve that. Ghidra does not handle kernel symbols very well, but there's ways to work around that. And in all of this, when you're staring at this giant, again, you're staring at Apple, and there's so much noise, you don't know what to do. Just kind of focus on that one CVE, and hopefully that will give you the insight that you need to understand the vulnerability or increase your RE skill along the way. I know that was really fast. It was 200 slides, guys, in 26 minutes. But that's it.